So this is where we left off, talking about Archimedes. We did quite a bit of his work with the spiral and with the circle, but this was something that is very, very exciting that was discovered at the turn of last century, 1906. This document, this religious document, very ancient medieval document, was looked at more carefully by a philologist, and he noticed that there was writing underneath the writing of the prayers and the liturgy and whatever the writing that was on top. And this was a very common thing. This is not something that's surprising. This was done all the time in the Middle Ages. Parchment was very expensive, and you took some piece of writing that was not very valuable, and you washed it off as best you could, and you used it again for something else. And since most of the writing in society was done by the religious orders for religious reasons, the writings are very much liturgical writings of that sort. And so the writings underneath, if that got lost, could be virtually anything. And this particular document here, he recognized, first of all, the diagrams, and by looking carefully, he could translate some of the Greek, and he recognized this as one of the known works of Archimedes. So what we had here was a document that was originally written, a copy of work of Archimedes, and it still was legible. What was most remarkable was when this thing was analyzed further, they found that, yes, this was all works of Archimedes, but there was one particular section or sections when you could put it together, which was unknown. This was not only something that was a document that was lost. Okay, we have things that we know Archimedes wrote. We have many things that we know Euclid wrote that have not come down to us. They have just simply been lost. But we know from other writings, later writings, that these things once existed. This document here that Archimedes himself called the method was unknown to the world until now. And so it was, obviously a tremendous find, really the most exciting find of ancient mathematics probably ever. And he describes this as the method as a way of getting an intuitive idea of what would be true, what intuitively the kind of theorems that you may want to try to prove properly, rigorously using the method of induction. And he says here that I presume there will be some among the present as well as future generations who by means of this method here explained will be able to find other theorems which have not yet fallen to our share. I love that expression, not yet fallen to our share. So I've left stuff for other people to do using this method. And as I said last week, this is very much the way the early mathematicians of the Renaissance and a little bit later were able to actually make their mark and to show that they were to be taken seriously, that they really were serious mathematicians by doing exactly this, by taking some work of Archimedes, for example, centers of gravity and other things that he did, and take a figure that Archimedes didn't work with and show show the center of gravity of that figure. Or take some volume that Archimedes did not work with and use the method of exhaustion to find that particular volume. And this was the way in which you proved that you were, a serious mathematician, to just do extensions of the work of Archimedes. And this was true going back even to the Islamic mathematicians before them. So here we have this document. And what is amazing about, there are many amazing things about the method, but what he's using here came to be called the method of indivisibles, which I'll explain as we go through two proofs from the method. But this was rediscovered in our era, in the era of the 17th century, by a student actually of Galileo, Cavalieri, who rediscovered this idea of indivisibles and used it to find volumes. And he did not have the benefit of the method. He actually had to rediscover Archimedes' method, as we'll take a look at two examples of. As I pointed out last week, what's interesting is Cavalieri and the other mathematicians right through to Leibniz, they were perfectly happy with the method of indivisibles. They felt that that was good enough. Clearly, it gives correct results. This is what Archimedes was saying. This is how you can get an intuitive idea of what the correct result is. But now you have to go ahead and really prove it. He actually states this, that now you really have to go ahead and prove this thing properly. The mathematicians, in the process of inventing analytic geometry and calculus, it was good enough for them to go ahead and go through what Archimedes would have called the intuitive argument. They felt that that was rigorous enough to establish these results. So here we have Archimedes being holding his work to a higher math standard of rigor and logic than we have of people, 1,800 years later. I do hope, if you haven't got a chance to look at one or two of the videos that I suggested about this document, this palimpsest, that's the word that's used for a document written over another document, and the tremendous work that has been done, the tremendous modern science has been applied to try to, get to see beyond the original writing and get underneath to Archimedes' writing, what they did using modern technology, never mind X-rays. I mean, my goodness, what they've done is incredible because of the importance of something like this, because of the importance of Archimedes in the history of mathematics. Okay, so we're going to take two examples from his method. And the first one we've seen before. This is our third proof of his quadrature of the parabolic segment. He's going to show that triangle, that central triangle that he uses to get the argument started with, that the parabolic segment is 4/3 of the area of that central triangle. But he's going to do it in a very, very different way, using his method. Here we'll get a chance to talk about indivisibles and see how this idea works. So we'll start the same way. We have our parabola, we create our straight line going across, we have our segments. The idea is to find the area of this segment, to find the quadrature of this segment, to find a piece, ultimately a square, that has the same area as this parabolic segment. If you find any rectangular figure, a triangle or rectangle, that's good enough, because you can easily turn any of those figures bounded by straight lines into a square. The idea for us is just to get this thing to be a comparable area to some figure, and what Archimedes is going to do, again, is to use a triangle. So he starts his construction. First of all, he takes the tangent line from one side. Notice the importance of the tangent line. One of the early questions we had in our course was, what's with the tangent lines? Why is this important? We saw, once we developed the ideas further and we got to rates of change and instantaneous rates of change, and where the slopes of tangent lines were those rates of change, now I can see from a physics or a science point of view why rates of change, are very, very important. But when you step back from that and just look at tangent lines, why is drawing tangent lines so important? Why was there so much energy devoted to that by the ancient Greeks and further mathematicians? Well, you see how the mathematicians use tangent lines, and we'll see many examples in today's class, both in Archimedes and in the subsequent presentation that we'll go through, where tangent lines continue to appear and are vital in the constructions and in the ideas that they're working with. Not the slopes of tangent lines. There were no slopes yet, right? There's no analytic geometry. Just constructing the tangent line itself is important, is of great interest to the mathematicians of the day, which called themselves geometers. They were primarily geometers. So we draw a tangent line, and then we take the other side and simply just draw a vertical line down, and they will cross at some point F, creating a big triangle, ACF. Okay. And he's going to go ahead and take AF and bisect it, calling it point K, and then draw a long line from C through K all the way out to H, where KH is equal to KC. So not only is K the midpoint of AF on the triangle, but K is also the center of HC. And that's going to be his lever. His lever is HC, and it's going to be balanced at this point K. He also points out that where this line going from C to K extended out to H hits his parabolic segment at B. He proves that that B, that's the point that gives him the triangle. That's the very point that if you draw the tangent at B, you'll get a line parallel to AC. He doesn't need that. He doesn't need the tangent at B, but that's the same point creating the same triangle, that little one, ABC. And he's going to show that the area of the parabolic segment is 4/3 the area of the triangle ABC. This is the third time we're seeing him prove this result, that one of his Pythagorean fractions of 4/3. Okay, so the area of the parabolic segment, that is the curved figure ABC as a curve, drawing the straight line back to A, that larger segment is slightly larger, 4/3, than the area ABC. What's the strategy of this? Notice I give, guys, I say it's the strategy of the demonstration. We're not actually going to do the proof. We're going to leave out many steps of the proof because they're quite algebraically intensive. We just don't have the time, nor did we say that we would go into that kind of algebra. So I'm trying to be careful. This is the strategy of his demonstration. We're going to try to follow his demonstration conceptually. And the only algebra that we'll use is at the very end, just to take your breath away, to show how simple and quickly this thing resolves up using the law of the lever. It's a simple algebra it is to finish the demonstration. So we have CH, this long line, this long red line CH. He's going to use this as a lever with the middle K as the fulcrum. And he's going to show that the entire area of the parabolic segment, whole area of the rounded segment, placed at H, he's going to take this parabolic segment and hang it off of H in his lever. That's going to balance the big triangle ACF, where it was just sitting right where it is. He's going to take the parabolic segment piece by piece, and this is where the individuals come from. He's going to hang them piece by piece from H, where the whole area of the parabolic segment hangs from H. But the area is a proxy for the weight, right? If you think of these things as thin metal pieces of sheet metal, all of the same thickness, and the area of these things is exactly comparable to the weight of these things. So he can talk about the area of these things hanging off of them using his law of the lever. Weight and area are exactly proxies of each other. So he's going to hang the entire weight, the entire area of his parabolic segment off of H, and he's going to show that that weight, that area hanging off of H, exactly balances with the fulcrum at K, the big triangle AFC at its center of gravity. Okay, because he's not going to move the triangle at all, but that triangle, all of its weight, according to the law of the lever, is centered at its centroid, at its center of gravity. The center of gravity of the parabolic segment will show you is H. That'll be very easy to see. But in fact, if the triangle, the big triangle, is still hanging where it is, where part of it is right up against the fulcrum, there at K, where is all of that weight focused? Where is the center of gravity pulling down for the law of the lever? Well, that's at the center of gravity of the of that big triangle, which we'll have to construct. Using that basic idea, he's going to show that the area, and two other things we're going to prove, that the area of the big triangle, the area of the big triangle, AFC, the balancing triangle, with his law of the lever, is equal to 4 times our triangle, ABC. Remember, it's ABC that we're going to show is 3/4 of the area of the parabolic segment. So it has a relationship between the two triangles. The red triangle is just 1/4 of the big one. We want to show that. And we also need to show where the center of gravity of the big triangle is. If we're going to balance weight, the area of the big triangle, we need to know where that center of gravity is, because all the weight acts as if it was at that one place that far away from K. Using all that, if we can pull all that together, Archimedes' argument will show that indeed the area of the segment, parabolic segment, will be 4/3 of the area of the small red triangle ABC. Okay, to remind you where the center of gravity of a triangle is, it's not difficult. This is right out of Euclid. You simply draw from the vertex to the center of the line on the other side. Take the vertex, draw it to the center of the opposite side. All these lines cross. Here's the red line is one of them also. Remember, we said that this thing was the midpoint at K. So yes, the center of gravity is where that point, where those three lines cross. So it's not hard to find the center of gravity. So according to the law of the lever, if he can do what he claims he can do, he's going to have the entire area, proxy weight, of this entire parabolic segment hanging off of H. He's going to leave the big triangle exactly where it is and show that this big triangle hanging from its center of gravity here at G exactly will balance at K. That's the strategy of his proof. What I just said, that last piece, that we're not going to show. That is quite intensive. That is, of course, the beauty of the proof, but we really don't have time to go through that. So if we can just see intuitively why this is so, we can finish off the proof that, in fact, the area of the parabolic segment is 4/3 the area of the red triangle ABC. Okay, just to review the preliminaries that we need. Remember the law of the lever. If we have something with a fulcrum here, and I have a weight here and a weight here, the law of the lever says they will balance if the weight times its distance from the fulcrum will equal the weight on the other side times this distance. So that's the law of the lever. I think we all know that. And since we have these symmetric figures, of course, the sphere is, a big piece. But if we know the center of gravity of the figure, the law of the lever works so that the weight is completely focused, completely acting from the center of gravity. So we don't have to worry about the whole sphere itself and where the individual pieces are. Just find the center of gravity, if you can, of these figures and just work with that exact place. Put all the weight at the center of gravity and then use your formula for the big G and little g. An example of that is here we have two things that balance, but we have two things on the other side. Not to worry, just find the center of gravity of these two pieces, given these two distances, find out where these two weights act as if it was just one weight at one place. And if they balance, sure enough, this weight times this distance will equal this combined weight, just the sum of these two weights, times this distance. And so an example of using the center of gravity of a distributed weight to use the law of the lever in a simple way, where you have one distance on each side. For example, if we had two figures like this, we tried to balance them here at A, well, it's easy to find the center of gravity of a nice symmetric figure like this cone, okay? Notice that figure is perfectly symmetric around its center point. So clearly the center of gravity is right here. Finding the center of gravity of this nose cone, not so easy, okay? This is the kind of stuff that Archimedes did, okay? Archimedes actually found the center of gravity, depending upon how this parabola would go out, how you spin it, how far out you have to go to find the center of gravity. Notice the center of gravity is not at the center. Clearly, there's much more mass, there's much more volume out here than over here, which where it's small. So the center of gravity is going to be leaning towards the thicker part of the cone. Exactly how you find this, Archimedes finds this using the method of exhaustion. But once you have the center of gravity, again, you can show that these two figures, as complex as this one is, will balance because this figure has all of its weight at its center of gravity. This figure has all of its weight effectively at its center of gravity. And if they do balance, as this picture shows, then this distance times this full weight should equal this distance times this full weight. That's the law of the lever. And finally, to find the center of gravity of a triangle, As I say, it is the centroid is just the intersection of all of the lines from vertex to the opposite side. And that is the traditional letter for that is G, and it is called the centrix, the center of gravity, the centroid of the triangle. And also you could, by the way, proves that there's a very nice relationship between this part of the line segment going from the vertex out to the center of gravity, and then going from the center of gravity out to the midpoint of the opposite side. They are always in the ratio of 2 to 1, okay? This is in Euclid, and Archimedes assumes his readers know Euclid, know that this fact. We will need this fact to finish off our law of the lever. Okay, with those preliminaries, oh, and so therefore the distance from E, this is going to be our fulcrum, remember, right? This is going to be our K. The distance from the fulcrum that we're going to work with out to the center of the gravity is actually 1/3 of the full distance from E out to C, okay? Because of this ratio that's proved in Euclid. All right, hold on to your hats. So here we are. I state again, okay, the strategy of the demonstration is using CH as a fulcrum with K as the, as a lever, with K as the center point as a fulcrum. We're going to show that the entire area of the parabolic segment, if we hang it at H with its center of gravity for every single piece of this thing at H, so we can truly say the whole weight is hanging from H, we need to see how to do that, that it'll balance the area of the big triangle ACF hanging from its center of gravity, which is here at G. We also need to point out that the area of the small triangle that we're interested in is 1/4 of the big triangle. That's really easy, guys. Again, we're not going to prove that. We're not going to take the time. But remember, if you take a look at this triangle, has the same base as the big triangle. And if this area, if this point here is 1/2 of the whole thing, it just has to show that this thing here, B, is 1/2 of that, which is easy to do. So clearly the area of this triangle has the same base, 1/4 of the height. It therefore is 1/4 the area. I've just given you the verbal proof, but we would have to show those 1/4. And he's going to use the law of the lever to show his result that the area of the segment is 4/3 the area of the red triangle. Okay, hold on to your hats. Here we go. He says, take any line through the parabolic segment. This is an indivisible. It's a line, it has no width, right? In Euclid, a line has no width. This has no area. But the idea of the indivisible is this is an infinitesimal piece of area. And that piece of area, we're going to take that infinitesimal little piece of area and hang it out on H. So we take that length, take it away, and hang it out on H symmetrically on both sides. So we know that that little piece of area is hanging symmetrically from H, because we got it. we put H in the middle. We put it in the middle of H. So it's hanging from both sides. So the center of gravity of that line is in fact in the middle at H. Okay. Now take that same line, but now draw the entire big triangle and leave it there. Take that indivisible of the big triangle and leave it there. Archimedes proves that the line hanging from H, the short line, the blue line, that's just the segment of the parabolic segment, exactly balances, according to the law of the lever, the longer line of the big triangle. In other words, he shows that the length of this line times HK is equal to the length of this line times HG. Times H times this distance here. Let me say that again. He shows that the length of this line times its distance from the fulcrum, HK, is equal to the length of this line times this distance from the fulcrum, this distance here to the fulcrum. He shows this for every single line. Let's take another one. We take this line here from the middle, and we also place it at H. We take the entire long line. He shows that this length of this line times the distance from its fulcrum is equal to the length of this line times its distance from the fulcrum. He does this for every single line. This is the part of the proof I can't show you, okay, because it would just take us too long. There's nothing here that we couldn't do. It would just take us probably a whole class or more to go through the algebra background that we would need, and we promised that we weren't going to go through that kind of difficult algebra. So let's take Archimedes' word for it that he can do this. So what has he accomplished when he demonstrates this is true for every single line? If we can think of these lines as the sum of these lines is the area, which of course is in a sense crazy because these lines have no area, they're just lines. But for every line of the parabolic segment, he has an equivalent line of the big triangle. And if you can think that the infinitesimal lines of the parabolic segment make up the total area of the parabolic segment, and all the infinite number of infinitesimal lines that make up the triangle make up the entire area of the triangle. This, of course, is ridiculous. This is only using the infinity principle of Strogas, but this is the heart of the calculus. And this is why Cavalieri and Leibniz were perfectly happy just doing just this, ending the proof with just the method notations. Not good enough for Archimedes, but good enough for them. If we've broken these two areas into these infinitesimal segments, and they're all balanced exactly, then what do we have? Well, defining our terms, let P be the area of the parabolic segment. Okay, that's the sum of all those individual lines hanging from H. Let the bracket triangle ACF be the area of the triangle ACF, and let bracket triangle ABC be the area of ABC. Okay. Now that I've defined my variables, don't blink because we're almost done. From the law of the lever, guys, here's the thing. Here's the thing in red. From the law of the lever, if you have agreed that every single line of the parabolic segment hanging from here exactly balances its equivalent line of the big triangle, then isn't it true that the total weight of the parabolic segment hanging from HK must equal the entire area of the big triangle hanging from its center of gravity, HG? That's the law of the lever. He has trapped the area P that he's looking for, the area of the parabolic segment, into an equation that he knows the other three pieces of. Don't blink because we're over. If you can agree with this formula, that the total area of the parabolic, as he hung it one point at a time, times its distance from the fulcrum, is equal to the area of the entire triangle that he never moved, hanging from its center of gravity, that all the weight is concentrated at the center of gravity, and he showed that every single one of these lines balanced, therefore the entire figure balances, therefore the law of the lever says that the entire area of the parabolic segment hanging here times its distance from the fulcrum is equal to the entire area of the big triangle hanging from its distance from its center of gravity. This is the formula. Don't blink. Isn't it true that the distance from K to G is nothing more than 1/3 of the distance from K to C? That's in Euclid, right? And that the centroid always divides that line, creating it into the interratio of 2:1. So this thing here is 1/3 of that thing there. Isn't HK equal to HC? We set it up that way. We made K the center of the fulcrum. Isn't HK the same as HC? Don't they cancel from both sides? Solve for P, and you're done. P is equal to 4/3 of the area of the triangle ABC. If you are not impressed with this, then you're a wonderful person, but you do not have any spirit of mathematics in you. If this leaves you cold, then okay, we love you, but you are not in any way a mathematician. This is an argument which, first of all, is unprecedented in history. No one ever thought to do anything like this before. And the simplicity of the structure of the argument is just breathtaking. The vision that this man has, and then to go ahead and do the detailed algebra that we skipped, to push it through to make it so. But the concept of this thing, using his law of the lever. Okay, well, questions? Anything, Mike, in the chat box? Anybody questions? Can I?
Nothing in the
I haven't
chat
totally
box.
overwhelmed you.
There's nothing in the chat box.
Okay, I've tried very hard to show the logic of this thing, guys, because I haven't one more to show you. We're not done. We're now going to do the sphere using volume. It's going to be the same basic idea. It's from the method. He's going to use the same idea of indivisibles, but instead of having infinitesimal lines, he's going to have infinitesimal coins. Okay, flat coins cutting spheres and cones, and he's going to do the same thing. He's going to balance a lever that he creates, and he's going to show his very, very famous formula that the area, the volume of a sphere is 4/3 pi r cubed. One of the most famous formulas in all of solid, probably the most important formula in all of solid geometry. Okay, so a little preparation for his work on the volume of the sphere. It comes from his real proof using the method of exhaustion comes from his masterwork on the sphere and the cylinder, where he shows that the volume of the sphere is 2/3 the volume of the inscribed cylinder. Okay, you take a sphere and you inscribe it inside very tightly around the cylinder. So the cylinder has the same diameter as the thing, it has a height of 2r, so the sphere just fits nice in time. He's going to show that the volume of the sphere is 2/3 the volume of the circumscribed cylinder. Another one of his beautiful Pythagorean formulas, fractions. He is so proud of this result. This is his, as far as he's concerned, the crowning achievement of his life is to prove this. And he proves it using the method of exhaustion. Then we discover 2,000 years later that he found this intuitively by using the method, his method, which I'm going to take you through right now. He thinks this is so important that he asks that this figure that you're looking at here on the left is put on his tombstone. And legend has it that this was the figure that was put on his tombstone to mark his grave. The story is that Archimedes was killed in the siege of Syracuse by the Romans when the Romans were in Punic Wars, taking over the Empire of Carthage, which Sicily was at that time. And he was killed by a soldier, even though General Marcellus made explicit instructions to go find Archimedes and bring him to me. He wanted to meet this man. Marcellus was a very educated man, educated noble Roman, knew the work of Archimedes, knew how important he was, and wanted to meet this man and certainly not kill him. The legend is that the soldier comes up to Archimedes. He's working on a diagram. He says, "You got to come with me. My general wants to see you." Archimedes says, "Don't disturb my circles. Get out of my circles." He's working on the ground in the dust, drawing figures. He says, "Get away from my circles." And then the soldier takes out his sword and kills Archimedes on the spot. This is the legend which has come down for us. That's been told a million times. We don't know what happened to that soldier when Marcellus found this, but apparently the people of Syracuse did honor his wishes and did mark his grave and put this cylinder on. The legend continues that 150 years later, Cicero in 700 BC is now an administrator in Sicily, in Syracuse, and he's there and he knows about Archimedes, and he makes it his business to go find the grave of Archimedes, and he finds it. It had been fallen and in disrepair, and it's been totally lost and covered over by God knows what. The legend is Cicero went ahead and got it restored and put it back into its garden shape and was able to honor Archimedes once again. And again, through history, it was lost and lost forever. So we do not know where the grave of Archimedes is. But that's the great story. I got to tell you the great math stories, guys. I'm sorry. It's my obligation to hand these stories down. And if you ever get the opportunity to hand the stories down to your grandkids, please do so. These stories are just the timeless stories of mathematics. Okay, Some preliminaries. What is the volume of this inscribed cylinder? The volume of a cylinder is equal to the area of the base times the height. Makes sense, right? You take the base and kind of bring it up the whole height and multiply those, you'll get the volume. Notice the base is just pi r squared, the height is 2r, and so the volume of the inscribed cylinder is 2 pi r cubed. Visually, if you took a sphere of water and broke it and poured it into the cylinder, it would exactly fill 2/3 of that. That's his theorem, and that the volume of the sphere is 2/3 the volume of the enclosed cylinder. It's kind of a visual picture of what that means. Well, the volume of the circumscribed cylinder is 2 pi r cubed. Therefore, you take 2/3 of it. If his theorem is right, 2/3 of 2 pi r cubed is 4/3 pi r cubed, and that's his famous formula. This is what we're going to prove. He proves this on the sphere in the cylinder, which is a masterpiece, using the method of exhaustion. We're going to see how he does it intuitively using his method. Here we go. He takes his sphere and he puts it into a larger cylinder. This cylinder is not the circumscribed one, it's much bigger. It's got a much bigger base. Here we have a sphere of radius r. Here the base is going to be 2r. And he also puts a cone in for good measure. Okay. So he has the fulcrum. This is the one difficult thing because of the way the picture is made. A is in the center of H and C. Okay, I know it doesn't look that way, but H is right up against the cylinder. Okay, the cylinder is hanging on one side, and he's got this point H dangling from the other side. A is truly in the middle of H and C, although it doesn't look that way because we've got the cylinder kind of at that angle. All right. This cylinder is bigger than what he needs to circumscribe. He wants the cylinder to have a radius of 2r, and therefore the cone will have also a base of 2r. So HA equals AC equals 2r. That doesn't show it. AC is the whole diameter of the sphere. So they are equal, although they don't look it. I warn you that one more time. It's also equal to the height of the cylinder. It's also equal to the height of the cone, and it's also equal to the diameter of the sphere. The whole sphere is 2r. The sphere is a radius of just r. So these are our dimensions. What he's going to do is exactly the same thing as he did with the triangle, except now he can't draw a line. His indivisible now is a very tiny infinitesimal piece of area. It's this infinitesimally thin coin, and he's going to take a buzzsaw and cut a coin in this figure. He's going to take that cut, take the coin of the cone, hang that out at H. It's called Q here in this document. It's H out here. It's going to take that coin of the cone and hang it out. Coin is nice and symmetric, so it's all going to hang from H. He takes also the coin of the cylinder of the sphere, the red coin, hangs that out at H, and he's going to do that for every single cut where he's going to build systematically the sphere and the cylinder one coin at a time, and he's going to take the large cut that these two come from, the cut of the entire big cylinder, and just leave it there. Same strategy as he has for the triangle. And he's going to show for every single individual cut, if you hang the cut of the cone and the coin of the sphere at H, that will exactly balance, that those two areas will exactly balance the area of the large cut of the cylinder sitting right where it is. And that's going to be true for every single cut. If you can buy that, we're not going to show that argument. We don't have time to show that. For every single cut, he's got two coins hanging out at H, okay? Center of gravity at H. He's got the cut in place of the big cylinder. He's going to show that they balance according to the law of the lever. And that the two volumes, so I'm sorry, the two areas added together times HA is equal to A times whatever distance out is to that real cut is, times the full area of the big coin making up this big cylinder. It's going to show this true for every single cut. Therefore, he's going to prove that the volume of the sphere is that famous formula 4/3 pi r cubed. Which notice, if you notice before the formula from the last slide, the volume of the inscribed cylinder is 2 pi r cubed, right? Not this one, this one's bigger, but the volume of the inscribed cubed is 2 pi r cubed. We showed that, and sure enough, the volume of the sphere, if you can prove this is the case, then this truly is 2/3 the volume of the cylinder, okay, which is what ultimately he wants to show. He's more interested in the 2/3 than he is apparently in the 4/3 pi r cubed, which of course is much more important to us as the formula of the real volume of such an important figure. All right, hang on to your hats. We're going to go through this one more time. Don't blink, because it's going to be over way before you think. Where is the center of gravity of the cylinder? That's easier than the triangle, guys. It's right in the middle. The cylinder is a symmetric figure. It's all hanging from the middle, okay? So the entire volume, weight, if you like, of the cylinder is hanging right here from A to M, which is exactly halfway from A to C, but A to C is the same as the distance from A to H. So all this weight out from A to H, all this weight here is hanging half, and this distance here of the big weight is only half as far away, okay? So we got these weights here hanging out this distance, AH, all the weight of the cylinder is only hanging out halfway out. Important, right, for when we apply our law of the lever. Okay. So we know that AM, M is the center of gravity, is only half of AH because it's half of AC, half the way out. Okay, we need that. What's the volume of the cylinder? The volume of the cylinder is the base times the height. The base is pi times r squared. R is 2r. So it's pi times 2r squared times the height. The height is 2r. So the volume of this big cylinder is 8 pi r cubed. Okay. Finally, this is it. Here's the equation in red. We're done. Okay, don't blink from here because we're done. If you can buy his coin argument, which I can't show you that's the beauty of this. For any of you people who are familiar with your algebra, go and find this proof and let your breath be taken away by the details of this proof. Let you see the godlike nature of Archimedes to show that this is the case, that these coins work out for every single cut. Isn't it true that AH, the distance out on one side, times the weight of the coin, the volume of the cone, plus the volume of the cylinder, all hanging out there at H, is balanced by the distance from A to M times the entire volume of the cylinder. If you buy the argument that this is true for every single cut, then by the argument of indivisibles, which is ridiculous, but it gives conceptually good answers, by the argument of the indivisibles, that all the volume has been accumulated in some crazy way using the infinity principle, that we've built up an infinite number of these coins to create these figures, that we have this balanced equation that hanging out here at AH is the two volumes of the cone and the sphere is equal to the balancing of the center of gravity AM times the volume of the cylinder. Are you ready? There's very little left. You have to know from Euclid that the volume of a cone inside is nothing more than 1/3 of the volume of the cylinder. Very pretty result, proved in Euclid. Of course, Archimedes assumes that we know our Euclid. Therefore, let us take AH and write it as 2AM. Yeah, right, AH is twice as big as AM. So we got an AM on both sides, they're going to cancel. And let's take the volume of the cone and write it as 1/3 the volume of the cylinder. Here we got volumes of the cylinder on both sides. Don't blink. Cross out AM, multiply the 2 through. 2 times the volume, 1/3 the volume of the cylinder is 2/3 the volume of the cylinder. 2 times the volume of the sphere is equal to the volume of the cylinder. AM has gone away. Subtract 2/3 of the volume of the cylinder from both sides. Divide by 2. But the volume of the cylinder is 8 pi r cubed. We agreed to that. The volume of the big cylinder is 8 pi r cubed. So the volume of 1/3 of it is 1/3 8 pi r cubed. Now divide both sides by 2, and the volume of the cylinder is 4/3 pi r cubed. Every time I see this, I'm I'm speechless. Again, the simplicity of the idea giving such a powerful result using these, where do these ideas come from? Who is this guy? You know, it's the same kind of reaction you get like when you listen to a great piece of music, you listen to Beethoven's Ninth, and you appreciate it, and you're moved by it and the power of it, and you study it, and you, even if you know music, you understand its structure, but still you say when it's all said and done, how did he think of doing that, to create this work, to put these notes together with this kind of orchestration? How did he do this? Well, you know, that's what genius is, right? We're not that. You know, you look at a painting, you look at the Picasso and the Guernica, and how did he think of where do these images come from that he can do this in his mind? You know, this is the kind of reaction you get when you see the David. How did Michelangelo conceive of such a work, the Sistine Chapel? Here's the slight difference, guys. There were symphonies before Beethoven. There were sculptures before the David. There were paintings before. This was never done before. There's no model for this. This is the model. This man is doing something never done before. He's not just improving, he's not making the greatest symphony of all time. He's creating the first symphony, and his creation is monumental. So I hope I've impressed you. Okay, before we go on, can I answer any questions about that proof? You can see the similarity of the concept there. Any questions? Have I left you speechless? All right, let's finish up Archimedes. I hope you feel this is worthwhile. I hope you feel that the time we've taken out to do this mathematics is worthwhile, to see the beauty and creativity of this kind of work. It's very rare to see this kind of work that can be approached to an audience like us, that we don't need advanced mathematics to understand conceptually what's going on. That's just the other part of the incredible charm of Archimedes. Okay, he's gonna then tackle finally the surface area of the sphere. He's not finished with the sphere. We've got the volume. The volume is 4/3 pi r cubed. It's 2/3 the inscribed cylinder. He's not done. He wants to prove, using the method of exhaustion, that the surface area of the sphere also has a beautiful relationship to that same cylinder. So he says in the method, he says, starting with the fact that the area of any circle is equal to a triangle with the circumference as the base and the radius as the height. That's our proposition 1. I'll show you the picture again. It occurred to me, it occurred to one of the greatest geniuses of all time, that just in the same way the volume of a sphere should equal a cone, whose surface area, the bottom of the cone, should be the surface area of the sphere, and the base and the radius should be the height. Notice the analogy. From the circle, he has the circumference using the base and the radius as the height. He said, we'll come to now the three-dimensional figure of the sphere. Then that should be a cone. The cone is like the triangle. And look at the cone, the base of the cone should be the surface area of the sphere, and the height of the cone should be the radius. It is exactly a geometric analogy. Here's our proposition 1. That's what he's talking about. That's the analogy he's coming from, that the area of the triangle, pi r squared, is equal to 1/2 the base, 2 pi r times the height r, which gives you pi r squared. He says, by the same analogy, the surface area, the volume of the sphere should be analogous with the cone as the area of the sphere is to the triangle. So what would be the analogy? The analogy is, well, the volume of the cone we know is 1/3 the surface area of the base times the height. Notice the surface area times the height. That's the volume of the cylinder. We know from Euclid that the volume of the cone is 1/3 of that. That's where this formula comes from. We've seen that. But Archimedes' analogous says is if my formula is right, the volume of the sphere is 4/3 pi r cubed. We know that. Then look, I can write down a formula using with the surface of the sphere. The surface of the sphere should be 1/3 the volume, the surface area of my cone, which I think should be the surface area of the sphere by my analogy, times the radius. So he's got a formula which he can solve for the surface area of the sphere. The surface area of the sphere should be the surface area of his base by his analogy. And so therefore the formula should be 1/3 the surface area of the sphere times the radius. And that's what he's looking for. You go ahead and solve that little formula for S and you'll get 4 pi r squared. That's his formula, okay? The volume, the surface area of a sphere is 4 pi r squared, another very, very famous formula in three-dimensional geometry. The volume of the sphere is 4/3 pi r cubed. The surface area, the painting surface area of a sphere is 4 pi r squared. He argues this by analogy. Okay, let's look at one more argument in the same way. Why is it that the surface area of the sphere can be exactly covered by 4 of these disks? And I hope you had a chance to look at that 3 blue, 1 brown thing with the beautiful graphics of showing, at least the graphics show that you can kind of take that cylinder and expand it out and see the relationship to the surface area of the two. It's nothing else, just to look at the graphics to get the idea. How is it that the surface area of the sphere is exactly 4 of these circles? Okay. Well, is there another way of seeing this? He says, well, look at let's go back to our wonderful circumscribed cylinder. Take a look at the surface area of the cylinder. That is just the can, not the top and the bottom. That's also 4 pi r squared. I think it agrees with my formula. Certainly we can agree that the area here is 4 pi r squared. He's claiming that the surface area is equal to the walls of the cylinder. Easy to see, guys, just cut the cylinder, flatten it out. Take your can with no top and bottom, give it a cut, and just flatten it out. What's the length? Well, the length is the circumference of the cylinder, right? The base of the cylinder. That's the length. What's the height? The height is 2r. Certainly the area of the cutout rectangle is nothing more than the height times the base. Well, the height is 2r and the base is 2 pi r. And so, yeah, the area of this cylinder cut out is certainly 4 pi r squared. So we can agree to that. But what does that 4 pi r squared have to do with these circles? Why is it 4 circles? We go back to proposition 1. Isn't it true that one of these circles is this triangle? Okay, it's the same area, pi r squared. Now take a look at our cylinder. Our cylinder has this length as the circumference of the cylinder when you cut it out, and it has the height of 2r. And sure enough, you can fit exactly 4 of those circles inside the cylinder. And so here's another analogy to show his famous formula that the surface area of the sphere is 4 of these circles, the shadow that the sphere would make on a wall if he's shown a light straight, a light very, very far away, just the shadow of the circle that the sphere makes. 4 of those shadows, it would exactly cover the surface area of the sphere. A very, very beautiful result. But one more thing, he's not finished. If you take a look, and so there's the formula again, 4 pi r squared, 4 of those circles, 4 of those triangles. He says, just notice one more thing. Go back to my can, go back to my cylinder, and put on the top and the bottom. Put the top on, pi r squared, and put the bottom on, pi r squared. Now the total surface area of the entire cylinder is now 6 pi r squared. It's 4 pi r squared plus the top and the bottom. So the total surface area of the cylinder, which circumscribes the sphere exactly, is 6 pi r squared. If I'm right, which I'm going to prove rigorously by the method of exhaustion, if the surface area of the sphere is 4 pi r squared, isn't that 2/3 of 6 pi r squared? Can't disagree with him on that. That's 6, 4 is 2/3 of 6. Isn't the surface area of the sphere 2/3 the volume, the surface area of the cylinder? So just as the volume of the sphere is 2/3 the volume of the circumscribed cylinder, by the magic of Archimedes, and it does seem like he wills this to be so, and the math just has to come along because he wills it. Not only does the 2/3 work for the volume, but the surface area of the sphere is 2/3 the volume of the enclosed cylinder, including top and bottom. I don't know. Who is this guy? Okay. Can I answer any questions or any comments about Archimedes before we leave one of the greatest geniuses in the history of math?
Peter, I just wanted to share, and Antonio posted that she was pleased that she thinks she followed most of that.
Wonderful.
So,
wonderful. That's a great compliment to me. So I worked very hard, as you guys know. It's wonderful. One of the wonderful things about teaching adults, as opposed to adolescents, whoever's, I do know my 7 years of teaching that you guys appreciate when a teacher, any teacher, not just me, when Mike is teaching, doing great work. I know he does with the bridge, that you guys appreciate when we try to go the extra mile and try to make this as understandable and interesting as possible, and try to really, I know you appreciate that, and that's what gives us the motivation. God knows it's not the pay that we get for doing this. All right. So
what I find interesting is all the years I had in math, up through differential equations and all of that, nobody ever explained this development of those thoughts.
I know it's called a
Which
crime.
I find kind of abhorrent that
It's called a crime. It's called a crime. It's the great crime of science compared to, imagine not knowing who Mark Twain was. Imagine who not having read Hamlet. Imagine not knowing who Faulkner and Hemingway is. We couldn't imagine that. You would not be an educated person if you did not know these things. What are you, some kind of a Neanderthal? Were you born under a rock? What kind of But go to one of the greatest geniuses in the history of mathematics. Go to a monument of his thought, and it's never even mentioned to people who study math. Are you kidding me? Why is that? Well, one reason is, you're too busy taking calculus and differential equations because we're training you as a physicist. We're training you as an engineer. We have no time for this kind of stuff. You want to go do this stuff, go be a math major. And then if you're a math major, make sure you go ahead and take a course in the history of math. When you take a course in history of math, you will get exposed to Archimedes. Only if you take a course in the history of math. You don't have to have, it's not required for a degree to get a degree in math, okay? This stuff is considered, why? Well, the justification, mathematics is this enormous science, right? It's this enormous body of knowledge. And there you are, there's a limited amount of time to train you to get whatever degrees you want, and there's just no time for everything, and there's no time for this kind of thing. So hopefully, as you get older and you have more time to appreciate, and you have time to read novels you never had a time to read, you have time to, go to art galleries that you never had time to do. Maybe if you're mathematically literate, you have time to go back and look at this stuff. I've been fortunate enough to be immersed in this stuff for so much longer, and has taken, had the pleasure of studying this stuff and beyond, studying the work of Euler and people like this and Riemann, and looking at their original works, so yeah, there. I don't know what to say, guys. It's just there you go. All right, this presentation here, we're going to go through all the work leading up from Archimedes up to Descartes. And then the next presentation will be on the differential calculus. We'll actually derive the derivative. We'll derive the algorithms to find the derivative. We'll see some examples. We'll do a max-min problem. We'll spend some time working with the derivative and seeing where this tangent line and the slope of the tangent line finally comes to be what we can think of as modern mathematics. It looks like I'm not going to have time to do my last presentation on the integral. It looks like it's going to take me, because we have this to go through and then we have the derivative to go through. It's going to take, through the next, our last two classes. We only have two classes after this. But I'm not, I'm okay with that, and I hope that you are as well. I think the videos certainly will, if you have the time to watch them, will fill in a lot of what's the rest of the story on the integral, particularly the connection. What's so important, what we wanted to get across, which we showed in the first presentation, was the fundamental theorem, the connection between the derivative and the integral that go between of the fundamental theorem. And I'll be showing you videos which highlight that and go through that argument again with the beautiful graphics. We will not get a chance to walk through it together. But I think you appreciate that there's no way, or I don't know where you would find the presentation I just gave you on Archimedes. Quite immodestly, there is baby stuff which just tells you that this is so, he did this and he did that, and he just tells you, they just tell you things. And then there's the real proofs, which are really beyond what we wanted to go, not beyond all of you, not at all, but beyond the limits we wanted to set for ourselves. And so I sat down to try to present something which would be appropriate for us. And I had to make that myself. And so I am most proud of that presentation we just gave. Among the many presentations I've given over the 7 years, I could easily put that one, in the top 5 of the presentations that I've worked on, felt really, something worthwhile to give to my students. So with that, I'm going to take the pressure off of myself, with your permission, to the pressure of finishing the curriculum, which all teachers are obsessed with, to finish the materials. I know you've all experienced, as I have, even in the core program, where the teacher is running through in the last class, just running through the last set of slides because they just feel that they have to get through it, and the whole thing was kind of a blur, and what was the point? Let's resist that and just keep going through at our own speed, at our own pace, trying to enjoy and understand what we have, and it is what it is. Okay. So let us, we have a lot of history to get through, and we're going to finish up the Greeks and then get up through the Renaissance with the development of the modern algebra that we can work with from the analytic geometry. So we start with this man here, Apollonius. He is a younger contemporary of Archimedes. Also studied in Alexandria. They probably undoubtedly knew each other. Slightly younger man, and his great work is on the conic sections. This has come down to us. The mathematicians of the Islamic period, the mathematicians of the Renaissance, the mathematicians of the 17th century, people like Descartes and Fermat and Newton and Leibniz and all the rest, Huygens, their classical education mathematics basically consisted of 3 things. You had to master the 13 books of Euclid, you had to master all of the extant works of Archimedes, and you had to master all the extant works of Apollonius. That is a minimum. If you did not understand thoroughly all of the works that were available of those 3 men at any time, you were not thoroughly trained. You could not get to the forefront of where mathematics was without having that as a background. And so that's the importance of Apollonius. He is completes the triumvirate of Euclid, Archimedes, and Apollonius. There are other important mathematicians in the Greek world, which we'll mention a few after Apollonius, but these are the big 3. Apollonius is famous not only for his work in the conic sections, he's also the one who's given us the different epicycle mechanism that Ptolemy used so effectively to create his solar system with the Earth in the center. And this device was also used by Copernicus. Yeah, he put the Earth, he put the sun in the center, but he still needed this device to adjust his orbits to get them to agree with the data. What data did Copernicus use? He used Ptolemy's data. He took very, very few measurements himself. He basically used also the Islamic measurements which were refinements on Ptolemy's measurements. So this also, this picture here that you see on the right. But I think I can just show one more slide, I think. That's his work in astronomy. Again, to answer the question about the importance of tangents, here's a great problem that comes down from us from Apollonius. He poses this question. Given any three figures, one of them being a circle, a line, or a point, or any combination, 3 circles, 3 lines, 3 points, find all the circles that you can which are tangent to those 3 places. So for example, suppose that we're given a point B, a line M, and a circle A. Here's a point, here's a line, and here's a circle A. Find all the circles which are tangent to those 3 objects. And you're tangent to a point if you go through the point. So look at this circle. This circle goes through the point, is tangent to the line, and is tangent to A. So it's a solution. Look at this circle here. It goes through the point, it's tangent to the line, and is tangent to A. So this is just a game of tangencies. And again, I show you this. It's a very, very famous problem that everyone worked on. Newton worked on this. He gave the complete solution to this. Yeah, Newton gave a complete compass and rule of solution to this problem, doing it for fun, I guess. And here's just an example of, here is 3 circles, and here are the red circles, which would be the answers. This circle is tangent to all of them here. They're all inside. I'm sorry, they're all outside the circle. Has 2 inside, or one outside, 1 inside, etc., etc. Here's an interesting one. Here we get 2 lines and 2 lines here. What do we have? In a circle. Okay, 2 lines in a circle. So this circle here is tangent to the 2 lines and tangent to the circle. Here's another circle, which is tangent to the 2 lines and tangent to the circle. So you can have a lot of fun trying to solve this. Of course, if you follow the rules, you can only use compass and straight edge to do this. Like I say, Newton gave a complete solution to this thing. So this is the importance of tangents that come down through the history of mathematics. We have time for one more. Here's another construction of tangents. Here's our parabola, which Apollonius did a whole treatise on, and he wants to show how to construct a tangent to any point on his parabola. And he says, well, draw the line directly over to the axis. Remember, he does have an axis. That's a valid thing. He has an axis to his parabola. He says, find out how far away that point is to the vertex and give me exactly the same distance the other way. Go take this distance and go right down the axis, the same distance. There's your tangent line. And he proves, of course, through formal geometry using Euclidean means that this line is the tangent, only touches the parabola at one point. So he shows how to construct tangents to lines. Again, just to show this is what these geometers were dealing with. Finding tangents to lines was very, very important to them for all kinds of reasons. And I'll end with just this animation. And I don't want to show this animation just to show off, but I want to make the point, a very important point. So here's the animation. Notice that no matter what point you pick, if you simply pick a point exactly equidistant away, you will get exactly the tangent line. Okay? Very, very nice. And this is true not only for this, our favorite parabola here, but we can go ahead and change, make it sharper, and notice that the same theorem holds. We can even fool around and turn the parabola upside down, and the same theorem. So this is a theorem of Apollonius to be able to construct a tangent line and take any point on your parabola, draw this line straight over, perpendicular to the axis, take the distance from the vertex. Of course, there's no x and y axis here, right? And in Apollonius, go to the vertex distance and just keep going the other side. And that's your tangent line. What I want to point out is this idea of this moving point is an anachronism. Okay, what Apollonius in his mindset, he's taking any individual point, take an individual point and make this construction, and you will construct a tangent line. He has no notion of the flow of this kind of thing. He has no notion that this point here is a function in any kind of way of this point here, or even simpler of this point here. Notice this point here is a very easy function of this thing. If this point here is -2, then this point here is 2. This point here is minus, a very, very simple function. This function would be more complicated. He has no notion, he has no need to have this idea of an association, a general flowing association. This is an anachronism. Okay, the only person who has any kind of a notion of this, the people who, worked with motions of locuses, which is, of course, Archimedes. So I don't want to give the wrong impression that this is how Apollonius thought of his theorem with this very nice animation. I show you this to kind of show a pretty version of the theorem to make it kind of more understandable. Okay, well, I apologize for that glitch. I probably will edit the YouTube before I put it out there and get rid of that craziness. So we'll jump away from that kind of thing. All right, are there any questions on anything before we go? Any questions, any comments? Are we doing okay, guys? Are we hanging in there?
Right. This is, again, my attempts to find a real world place for all of this. Looking at this, would this be the kind of math you would need to be able to construct navigation?
It certainly is the beginning of it. It's certainly the basis of it. Certainly navigation and all those other applications of mathematics come from this kind of mathematics. That's for sure. It comes from the basic geometry of the Greeks. But then you focus on particular problems. You focus on problems of surveying. You focus on problems of navigation. You focus on problems of astronomy, of mapping the sky, and you apply this geometry and you develop new methods, more powerful methods based upon this kind of stuff. So certainly this is in the right direction.
Thanks.
All right, so I will end our class. I'll stop the recording and we'll see you next time, guys.